Uh, so is it visible there?
Yes, visible.
Okay. So I'm going to start.
Okay.
Good morning, everyone. I am Samayat from IIT Kanpur, and I'm going to present a brief lecture on impact modeling using Abacus CAE. So this is lecture 2, which is the continuation of lecture 1. On lecture 1, I presented the impact modeling for isotropic material. So this is the second lecture. So the objective of this lecture is as follow. So I start from problem definition. So impact modeling using Abacus CAE. Uh, the problem definition is as follow. The model contains a rigid spherical impactor of dimension 40 millimeter diameter and a target plate of 150 by 100 by 2 millimeter, which is considered as deformable plate. Both are modeled using Abacus computer aided engineering, and the laminate is stacked in such a way that 019 symmetry. So we are going to use four laminas of stack. So this tutorial lecture covers a basic example of a spherical shaped projectile being fired at laminate composite plate. It needs some knowledge of composite material and the basic knowledge of Abacus CAE. So here I am not going to tell you about the Abacus CAE and the working principle, but basically how Abacus CAE works for the impact modeling. That is the case. So this tutorial will take you all the important steps required to create the model and run a basic Abacus simulation using Abacus CAE and to visualize the result. So we start from the basic modeling, and then finally we have to see or visualize, run the program, and then finally visualize the result. That is the intention of this lecture. So to start our work, we begin with the basic steps, which involved in the creation of models in Abacus CAE. Uh, so the first thing is we have to open the Abacus software from our PC or from our computer, and then we start with the standard explicit model, because we have a number of options on that. That is with the standard explicit model, with electromagnetic, with CFD modeling. So this, we use a standard explicit model for our purpose. So then on that, the first thing is uh, I can start directly. I have to start with some model also. Let me go to the Abacus software. Okay, let me open the software, Abacus CE. So as I open the Abacus software, we can see this screen. On that, we click on with standard explicit model. So this is our what I'm saying. And then the next one is the next is set the work directory for the proper data saving of the particular project. So whatever we are doing must be saved in one particular folder. So for that, we have to set a directory. Okay. And then we have to save our file to that directory. So set directories first, then save it to the directory with some name, any name you can give, so that it can be impact simulation. That may be the name of the file. And then to run simulation in CAE, you can either work with the various modules in the drop-down menu at the top of the screen, or you can click on the menus in the workflow trees on the left-hand side. What are the, let's see this thing. So this is our Abacus working environment. On this Abacus working environment, we have two different options. For example, we have a workflow tree here, and or we can use the modules, different modules here. For example, part module, property module, assembly module, step module, interaction module, loads module, mesh module, job module, visualization, and so on. So we'll see this one by one. So all these things are available here. Everything is available here in the workflow tree here. Part is here, material is here, assembly is here, that step is here. Again, load boundaries are here. Job is also here. So all these things are available here. Someone can use this one, or someone can, another person can use this one, both having the same function. Okay, so let me use with the module part. So this is the Abacus working environment. This is the working area of sketching area. Okay, so this is main menus. And these main menus will change from module to module. As we go from part module to property module, the main menus immediately change according to our requirement. In property module, we need material section, other things. And if we switch it to the assembly module, the main menus also immediately change. It changes. Again, if I change to step, it also changes. So Abacus gives access in every module the required main menus. Okay, so our aim is to start with some basic geometric creation. So part module is the first module. Okay, when I go to my slide, so we can use any of this thing, either workflow tree or module. So these are what I have discussed, the modules in Abacus that are part module that used to sketch the dimensions and create parts or components. Property module helps us to create material properties and assign material and section. The third one is assembly module, which enables us to assemble different components and to make some transformation things, that to place the object in a proper position, we have to rotate or translate or other thing, and so on. The step module helps us to identify the analysis type and to introduce the required outputs. The analysis output will be given through the step module. And also interaction module will help us to make for interaction between two connecting or two parts which come in contact. Okay, so interaction model also helps us to constrain some parts. Next, load model. That load model helps us to create boundary conditions and to create different loads. And the mesh is to discretize the given domain into the required analysis domain, which helps us to assign the finite element mesh. And then job module helps us to run and monitor the job while running, and some other activities also. And finally, visualization module, which helps to visualize and extract the output of the particular analysis. Okay, this is a simple working environment of Abacus. Okay. So the first step in our modeling is creating the parts. Different parts which are used in assembly are created in the part module. So we have to create two parts in this case. The first part is the plates, and the second part is the impactor. So plate dimension is already given, and the stacking sequence of the composite plate is already specified, so that we will create two plates of dimension 150 by 100, and the thickness of each lamina. Here the plate is lamina actually. In the case of um, isotropic material, we used a single plate, so that we call it as plate. But here we are going to stack four laminas together in order to get a laminated plate. So that a laminated plate, 2 millimeter dimension with four stacks, so that we divide the 2 into 4, that is 0.5 millimeter thickness each stack, because that means each lamina. So we'll go to the part create module. So let me go to the practical one. Here, this is the, we are in part module. Now I'm clicking on the create part. Okay. Then I can call it as lamina 0. For example, I'm going to create 0 lamina, because our lamina contains 0 and 90, and the 3D deformable solid extrusion. So the thickness of the lamina will be given by extrusion, so that extrusion. And our lamina is considered as deformable material. So, and I'm going to use metric system, okay, completely meter unit system, so that there will be no confusion on the work. Okay, so now, on this working environment, in our working screen on the grid, I'm going to sketch a rectangle. So we have a number of geometric entities here, starting from point to some other curved profiles. So point is there, line is there, circle, rectangle, ellipse, and other spline curves also there. So that, let me start with a rectangle. So I clicked on a rectangle and simply draw a rectangle here on the screen. Once I draw a rectangle, then I have to give dimension. For that, there is an add dimension option here, add dimension. Click on horizontal line, then give the dimension, that is 0.15 meter. Because it is 150 millimeter, means 0.15 meter. Yeah, then I have to select the vertical line, and that is 0.1 meter. Well, that is 100 millimeter. Okay, then zoom in. We can see this rectangle, and I want to bring this rectangle to the center. For that, I will draw construction line. Okay, so then I have to copy it to the center of the grids. So let me move it. Yeah, not copy, but move. Yeah. Then click on the center and bring it to 0, 0 location, then zoom in. So this is our rectangle with 150 millimeter by 100 millimeter. And then the thickness will be given by extrusion option. So that let me go to the extrusion, click on done. And then here it asks us to exit base extrusion or edit condition. So depth I am going to give that is 0.5 E minus 3. That is the thickness. Now this is the one lamina, which is 0 lamina. And we need another lamina also, second lamina, that is 90 lamina, so that I can copy it or I can create the new one. Okay, so we can copy it from here, from part 0 lamina, copy and give name another name. But for our simplicity, let me copy it from here. Copy. Okay, then lamina 0 copy. Rather than I'll give name 90. Lamina 90. Then okay. So now we have two laminas. Lamina 90 and lamina 0. So these are the two laminas. And the next is creating second part. That is the impactor. So the impactor is considered a rigid, discrete rigid impactor with diameter of 40 millimeter. So that I'm going to create impactor. How can I create impactor? Again, in the same part module, I'll click on create part. Then by default is size part 3. No, it is now, yeah, it is part 3 because lamina 1 and the 2 created. Okay, so let me call it as impactor. Name impactor. 3D, okay. Rather than deformable, I click on discrete rigid. And then I want to create it from shell revolution. So I click on shell and revolution. Okay, then continue. Then from the geometric entity, I'll click on the circle. Okay, circle. Yeah, circle. I'll use 0, 0 position. Okay. Now to identify the diameter, that is 7 millimeter diameter. 7 E minus 3. This is the circle with diameter 14 millimeter. And now I will perform some other operations on that using line command to bring the shape of the impactor. Then I have to trim the lines which are not required. So there is a trim option here, trim this line. I don't need this line, I don't need, and this quarter. So we have left the half section of the profile of the impactor. So I want to revolve this section into 360 in order to get full size of the impactor. So for that, let's done. And then angle, I'll give you 360 here, rather 90. So immediately an impactor with 360 revolution is made. Okay, once this impactor made, this impactor is a rigid body, so that we have to give the reference point for the impactor. We have to give a reference point for a rigid, discrete rigid geometry. So for that, tools, a reference point, then the reference point, let me select this point as reference point. Okay. Yeah, immediately it shows some RP. That implies that reference point. So now we created two parts. One is uh, two plates, and the second one is the impactor. So the part creation, create part is already done. So you can see this slides will tell you how to draw this quantity or these objects. Okay, how to create the plate and how to create impactor are already specified in this two slides. Okay, yeah. Then the next step, the second step in our modeling is defining material property. So in last lecture, for isotropic material, the material property are very easy. That is only the Young's modulus of aluminum and the Poisson ratio and density. These are sufficient because the material is considered as isotropic material. But in this case, the material definition is very tricky because the material is not isotropic in this case. It is completely anisotropic, and we have to define different material property. And also, the failure condition of the composite material is completely different from the failure situation of the isotropic material. So we have to define the failure property, the fracture, the strength properties. Okay. So for that reason, the materials here, required materials are the elasticity property, the strength property, the fracture energy, and the density are required. And when we come to elastic property, we need different properties. The 9 elastic properties, the 6 strengths, not only 6 actually, we can consider the Z thickness direction also. So, and the fracture energy, and also other properties are also needed, which are not included in this lecture, like the interface properties. Interface properties are not included in this lecture. So whenever we consider the delamination problem, the interface property also will be included, and that will be added. So I'm going to use the material property of T700M21 carbon epoxy material. So for that, we have to switch to the material module. So how we can do this thing? For example, the material properties is Young's modulus in one direction is 130, in two direction and the three direction is 7.7 gigapascal. The Poisson ratio 1, 2 and 1, 3 given 0.3. The shear modulus 1, 2 and 1, 3 is given as 4.8 gigapascal. And the shear modulus in 2, 3 given 3.8. This is for T700M20 carbon epoxy material, particular material. And the strength properties are taken or experimentally prepared as tensile strength in the fiber direction is 2080 megapascal. In compressive fiber direction, 1250 megapascal. And the tensile direction in the Y, that means in the transverse direction, which is 62 megapascal, and compressive in the transverse is 240 megapascal, and the shear strength in the 1, 2 and 1, 3 direction 110 megapascal, and the shear in 2, 3 are 80 megapascal. And the fracture energy is given as 133 Newton per millimeter. That is the G1 tensile. That means in the fiber direction, tensile in the fiber direction, compressive in the fiber direction, the fracture energy is 10 Newton per millimeter. In the transverse direction, the tensile one is 0.6 and the compressive one is 2.1. And the density of this particular material is 1,600 kilogram per meter cube, not millimeter, but it is meter cube. Okay, so this is only meter cube. Okay. Yeah, so these properties must be introduced to the abacus system. So now let me switch my module to the property module. Okay, on the property module, here we have a create material. Okay, then on that, give the name of material, let it be composite material. Then click on general, then density. On density, provide the value of density. Okay, that's 1600. Because I'm using matrix system, so I can use directly the number itself. The next is mechanical property. So elasticity, mechanical elasticity, sorry, and then elastic. When I click on elastic, we have a number of options. As we have seen in the last lecture, for the isotropic material, by default, it gives only the Young's modulus and Poisson ratio options to fill them. But now our material is not isotropic, so that we must give either laminar property or engineering constant. So for that, I have to click on this, and we have this many options: engineering constants, lamina, orthotropic, anisotropic, traction, shear. So let me use engineering constant. Okay. So this engineering constants E1, E2, E3, these values are already what we have discussed. So E1 is 130 gigapascal. This one is 7.7 gigapascal. This one is also 7.7 gigapascal, 0.3, okay, 0.3. And this mu1 23 0.36, and G12, which is shear modulus, which is 4.8 E9. This also 4.8 gigapascal, and this is 3.8 gigapascal. So these are elastic properties. Okay, so once we fill elastic property, this is a fiber reinforced matrix. Fiber reinforced matrix. So we have to define the strength properties and the fracture properties. So again, let's go to mechanical, then damage for fiber reinforced composite, because this is fiber reinforced composite. And then it by default gives you the hashing damage. That hashing damage is the damage that defined by Hashin in 1980s. He proposed, he formulated the damage mechanism of fiber reinforced composites. That he proposed damage in tension, damage in compression, either for both fiber direction or in the transverse direction. That means Hashing damage, matrix compression damage, matrix tension damage, fiber compression damage, fiber tension damage. These are proposed by Hashin in 1981. So Hashin damage selected, and then in alpha is there that considers the shear strength of the shear 1-3 direction. For that we give 1, or we can left it as 0, but let's use 1. So it lies in between 0 to 1. The value is either 0 or 1, or it lies in between. Anyways, so now longitudinal tensile strength, which is already given as 2080 megapascal, that E6. Longitudinal compressive strength 1250 E6, that megapascal. Transverse tensile strength, which is 62 E6, and transverse compressive strength 240 megapascal. Longitudinal shear strength, that is 110 megapascal, and this is 80 megapascal. And then how we can define the damage or the fracture energy? Let's go to option here. On the same tab, I will go to option and then damage evolution. So on damage evolution, it allows us to use the energy, evolution type energy, softening linear, and the fracture energy in the tensile direction, fracture energy in compressive in a direction. So longitudinal fracture energy, which is given 133 uh, Newton per millimeter square its size. So that to account it for meter, I will give E3 here. Why? Because I'm going to use Newton per meter dimension. And this is 10 E3, 0.6 E3, and 2.1 E3. So this linear softening indicates that once the damage, the Hashim criteria is fulfilled, and once the material damage is initiated at some point, from that point onward, the stiffness of material degradation starts. And that stiffness degradation considered in the linear manner. So that is the meaning of this linear softening. Okay, so all the material properties are defined here, and we are not using the interface element, so that I'm not going to define it. So, okay, so this is only for the two plies. But what about the material property of the impactor? So our impactor is discrete rigid impactor, so that mass is sufficient to define for impactor. No other property required. Sometimes we might define other properties like the material on which that impactor made. But for this, only mass defined through the mass center of the geometry of the impactor. So how can I define the mass? Let me go to, now I am in property module. So special inertia, create point mass, continue. So I'm going to select the reference point to assign the mass. Then, and let's take some 3.132 kg of mass. I'll use only numeric value, not the unit system. So 3.132 is the mass, and which is assigned to the reference point. Okay, then say okay. So we can see some green color here on the impactor. That indicates that mass is assigned to that particular point. So now the next is assigning property for plate 90 and plate 0. How can I do? We already defined the property. So we can use different options. We have an options to create section and assign section options. So now here we are going to use continuum shell element for modeling this thing. So that for continuum shell element, this create section and assign section option will not allow us. Okay, so that we have another two options for the composite. The first one is using the composite here, and another one is using the layup here. Both will lead us to the same position. So let me use this composite option. Create, okay, composite, create. Now I want to model each play as a single play so that this three will be, initial play count should be 1. Okay. And let me select, we have an options to select continuum shell, conventional shell, solid shell. So let me use a continuum shell, which mostly we are using. Okay, continue. And here, it allows us to give the name of the fly. The first fly is zero fly. Okay. Okay, I will give the name zero. Zero. The region on the fly is this region, done. And the material is composite material, which we already defined it. Okay. The relative thickness also, I can use that 0.5 as a relative thickness. Okay. And then the angle for the first fly, this fly is zero fly. So zero lamina, so that I will give zero. And the integration 0.3. Okay, that is done. Okay. Immediately the zero ply is changed from white color to green color. And then let me do the same thing for lamina of 90. Okay, name let it be 90. Region, this region, material, this material, and thickness, and angle 90. Okay, so we can see it immediately changed the one direction to vertically upward to y direction. Previously, in the case of zero, it directed towards to the x direction. Why? Because the fiber is oriented to x. But now in the 90 case, the fiber is oriented to 90 degree to the horizontal. So that is the orientation is also defined, material is defined, everything is now defined. Okay. So this is, the play is now done. Material properties of both play and the impactor is given. The next module is the third one is the assembly module. Okay. So material definitions already done. Assign these materials. Okay. Everything done. Okay, these are the steps. Defining impactor mass already defined. And the next one is create an assembly. That is the third step. So we have to switch to the assembly model, click on instance, then select plate 0, then apply, select plate 90, apply, select plate 90, apply, because that is, our plies are symmetric. It is symmetric ply, so that it is arranged as 0, 90, 90. Let me write it. Pointer, keep in, okay. 0, 90, 90, finally 0. That means 0, 90 symmetric means this one. So so let me do this thing. Let me switch to the property module to assembly module. Now I'll click on create instance. Then on the create instance, I'll click on 0 first. This time I have to check the radio button of auto offset, because that helps us to get separate objects. Unless and otherwise, the objects will stuck together in one place and will make us confused. So that let me do this. Yeah, then apply. Uh, the second is 90. Apply. You see, it is now in separate position. Apply. Again 90. Apply. And 0. Apply. Finally, impactor. Okay. So we have 4 plies. 1, 2, 3, 4. These 4 laminas will be stuck together to get the required dimension. So let me stack them. How can I stack them? I have to move this one over this one to this, and so on. So let me translate this one. That is, we can zoom it and select this point, and also so at this point, now 2 plies are stacked. Again, the third one. Take this point, bring it to here, and the fourth one, move, zoom it, select this point, yeah. Now 4 plies are made, and let me bring the this impactor to 0 position first. Then to 0, 0. So impactor is in, it is 0, 0 position. So this is the stack of 4 ply and impactor. Now the impactor needs some transformation or translation, not translation, but rotation about x-axis. It has to be rotating the x-axis in order to erect in proper position. How can I do? Rotate, click on impactor. Then we can take 2 points in the x-axis. Okay. Someone use 1 point here and another point here. So this is axis of rotation, and by default it gives us 90. Let's check. So that is in negative direction, so that let me give minus 90, minus 90. Now the impactor is erected to proper position, then okay. So this is the assembly of our system. Yeah, this is assembled. Yeah, now assembly is done. What is the next step? So the next step is the step module. Anyways, let's see. So this is the assembled situation on my slide. So the fourth step is defining the step. So this is the defining step. What it works for us. So which specifies the time interval of the simulation. We can specify time interval on this. Again, we can specify the analysis type. Again, we can define different outputs that either history output as well as the different outputs will be specified through this module. So the step module also helps us to define the variables that will be saved to the output database during analysis. In the so for that, select the step module first. Then from the top menu, select step create. In the menu data pre, select dynamic explicit. That dynamic explicit is our analysis. Someone can use static analysis. Someone can use dynamic implicit analysis. Someone can use different type of analysis. We'll see them one by one. So then on the next, in the explicit, make sure that this non-linear geometric thing is switched on. We have to switch on this thing because automatically the Abacus system switch on for dynamic explicit. But in some other case, it may not. It may be off. So give some time period. For example, I used 0.06, that means 6 milliseconds in my case. Depending on your analysis type, you can use more than that, this or less than this. If the analysis is very fast, you can use a very small microseconds. But if the analysis is like less speedy, then we can give less higher time. And for static analysis, it is very higher, even in the seconds. Okay. So the step module also allow us to select the variables to write to the database, and it will also helps us to create different outputs. So how we can use it? Let me open the model. So let me switch my model to step module. Now I am in step module. Uh, Click on create steps. Now they give the step as impact simulation step. Let it be impact, and then here by default it gives static general, but this is not static analysis but dynamic. So let me select dynamic explicit and make sure that this procedure type is general. So here we have two options, general and the linear contribution. So make sure that you are in general. Okay, so dynamic explicit in general procedure. So continue. Then here non-linear NL geom is on by default. And then I will give some time 0.006 and the remaining setting remain the same. Then okay. So uh, the next is here we have different outputs, field outputs and history outputs. Okay, so by default, as we select the analysis type, there is some outputs already there. We can leave them as it. We don't touch it. It can be as it, or we can eliminate some of unnecessary variables from them. Anyways, these are as it, but we have to add some others. For example, the I need to float the velocity of the impactor, uh, displacement of the impactor, as well as the plate, and the reaction forces on the plate. So for that, I have to give some other outputs. For that, let me define some reference point to the impactor. Tool set, let me set it first. Tool, set, create. Okay, let me call this, the name of the set as ref, means reference. So that output reference, I'm going to extract some output through the reference. So let me use the ref point. Done. So let me create the output. Okay, create, continue. Through the, let me select set from here, domain, set domain. the set is ref, that reference set. Okay, so through this reference set, I need to have U3. I want to float U3. I want to float V3. Okay. I want to float reference, no, the reaction force. And then switch on the status from state field user time, go to status, switch on it. Now, this is one of our output that is switched on. And we have remain some general contact outputs, that the contact between the plate and the impactor, what is the contact force and the pressure on that surface. That will be extracted later. For that, let me go to the contact interaction and then come back to the step module. Okay, so that is what. So I created set and reference point, and then using the reference point, I created some yeah. So the outputs from display velocity acceleration, I check these things, U3, UV3, A3, RF3, and so on. Okay, that is what it is saying. So the next is contact definition. Now we have two contact definitions are required. One is plate-to-plate contact definition, and another one is the impactor plate contact. The plate-to-plate contact definition helps to join the plates as a single material, even though they stacked material. It helps them to join as a single plate. And the plate impactor interaction helps us to make impact properly in a prescribed position and make separation and make the same thing. So such type of relations are required. So how we can do that? For that, go to the interaction model, then define properties of the contact on that. For that, interaction property create, name the property as some general contact, and then go to mechanical normal behavior. So accept the default setting, go to mechanical tangential on the same place, I think. Then select penalty friction. Some people can use frictionless contact, but for our purpose, let's use a penalty friction of 0.3 and then press OK. Then specify the surface that will make contact to each other. So the next is we have to make a tie between the two plates. Plate to plate must be tied together or made with some general contact. So what we can do, interaction, find contact pairs, tie constraints for the place under contact. And then define surface as a top of laminate and outer surface of impactor. For the impactor laminate interaction definition, we have to define surface first. Okay, we have to set or define surface and then make a general contact for the two surface. Okay, how we can do that? Let me go to the model. So let me switch to interaction model. On interaction model, I have to define come to create interaction, general contact explicit. By default, it says int1. Okay, let it be as it. And go and here, select on create interaction property, contact, continue. Then we can find mechanical here. Mechanical, tangential behavior. Here in the tangential behavior, by default, it says frictionless, friction formulation and frictionless. But in our case, we need some friction on the surface. Okay. But some guys use the frictionless contact, and then finally surface to surface, that finite sliding surface to surface contact. But here I want to use penalty friction of some 0.3. So I click on penalty, then friction 0.3. Again, let me go to normal property. Normal property, I will take as the default setting, that is pressure over closure, hard contact, constraint reinforcement, default, and allow separation after contact. So this is taken as a default. Okay. Then, okay. Now, let's make the interaction of the plates. For that purpose, let me make some gap between the impactor and that plate, unless it will disturb us. So let me give a small gap between impactor and the top of plate. So I come back to assembly. So let me move the impactor from this position, uh, impactor from 00 to some 0.001 millimeter, that in the minus z direction. Let it be, yeah, 1 millimeter from in the z direction. I allowed it to move up. Now it is separated, and finally I will bring it back to its position. Okay. Now, okay, I'm here just in interaction. So click on find contact pairs. We can see this screen. Okay, here I will click on find contact pairs. Yeah, we have three contact pairs. We have four plates and having three contacts. Okay, the contacts are n minus one. The number of flies minus one. So, okay, this contact, uh, 0, 90, 90, 90, and 90, 0 contact. So the type of contact, let me make it as tie contact, tie constraint. I'm making constraints. So now the plies are tied to each other. We can see it here. We can see what it, the constraint to each ply. They are considered as a one unit of system. And okay, okay, then, okay. So we can see some circular dots that shows the constraints of the thing. And I have to also constrain the impactor also. That how constrain impactor? Create constraint, uh, rigid body, continue, and body element. Click on edit selection and select the impactor. Okay, and then reference point. Okay, click on this and show the reference point. Yeah, then okay. So the impactor also now constrained. Okay, this is constraint is done. Now let me define two surface first. So tools, surface, create. Let me call this surface as tool top. Tool top. Tool top means impactor top surface. Continue. I'll click on the parts which are going to make interaction with the top of the plate. Yeah. Now it asks which surface is our preference. So our preference is the outer normal surface, which make contact with the plate only. So that is the brown color. The purple color is inner one and the brown color is the outer one. So brown. And also I have to define the surface of top surface of the plate. Tool, surface, create, then plate top. So plate top surface is this surface. Okay. This surface will make contact with the impactor so that done. Two surfaces are now created. So let me go back to the uh, interaction manager, edit, and then go through this individual property assignment. So click on edit, and then this plate top, tool top, and the plate tops are uh, going to give. I'm going to give the interaction property for these two. You see this? Yeah, the red color, because I clicked on highlight selected regions. So now which are created with frictional contact of that zero point 0.3, that is interaction property. Click on this and then um, select this. So we have this interaction. Yeah, it is created now. Okay. So one interaction is created, that is the surface of the top surface of the plate and the top of the impactor. So interaction is done. So as I told you at the very beginning, I will go back to step module to define the interaction properties. Okay, means the output from the interaction. So for that, I'll click on the history output. Okay. Uh, we can give name the interaction output. We can call this as interaction output, or we can leave it as it anyways. Then click on this. What you can see here, general contact surface interaction. If our interaction is surface to surface interaction, we select on interaction. Now we made general contact, so that I will select on general contact surface, and I'll select the general contact surface as plate top. That is the general contact. And what output I want from this top, I want the total forces due to contact pressure. I want total force due to friction stress. I want total force due to contact pressure and frictional stress. So that I have to click on the F3 component is enough for us. I don't want all of them. F3 only, the third, that the Z dimensional one. And then the surface areas in the contact should be selected. Okay, so this is what. Now the output request is already done. Interaction is done. What's left? Okay, what's left? Nothing. Yeah, all important, these alternative definitions. These are general definitions actually. Okay, these alternative definitions are for the surface to surface contact case. Okay, so constraint is already done. Now, the sixth step is the load and the boundary conditions. The load, boundary conditions, and initial conditions. So how we can do? We have to specify loads, we have to specify boundary conditions, and the initial conditions of the analysis. For that purpose, we have to switch our system to the load module, and then we'll make a practical work rather than you can see this slide. But let me go to the Abacus model. So let me switch to the load module. I'm now in load module. Okay, here What can I do? I have to support the plate vertically because when the impactor hits, if it is not supported, it will go. So, in order to fulfill the experimental real situation, I have to give either clamped or simply supported boundary condition to the plate. Because this 150 by 100 size plate is taken from the real size of the structure, which is fixed on the structure, so that it may be, if we consider it as a wing, then it is considered some simply supported. And if it is considered as the fuselage of the aircraft, it may be fixed because on the fuselage, the structure is fixed to each other. We cut the cross section from that. So let me use simply supported condition. Okay, for that, click on create boundary condition. Okay, here I can say simply supported, or I can say 4S. Okay, and then symmetry, anti-symmetry in caster under mechanical, and then initial. So this under mechanical continue. Then I'll select all the four edges of uh, uh, the plate, the four bottom edges. These are all the bottom edges of the plate. Yeah, now done. So this is pinned. I'm considering the simply support boundary condition that all translational motions are constrained except the rotations. If I encounter it is fixed boundary condition, all rotational degree of freedom as well as translational freedom will be constrained. But let me use pinned boundary condition. Okay, so now this is what the boundary which supports the plate. At the same time, I want to constrain the impactor only to move in the Z translational direction only. So let me go that Z motion, let me call it as Z motion, and then displacement, mechanical under initial step, okay, continue. Then I will constrain it because this is a rigid body, it is not deformable. So I'll use only the reference point. So I'll constrain it through the reference point only. I'll click on reference point of the impactor. Okay, done. Then we can see this dialog box. On this dialog box, we switch on this U1, U2, UR1, UR2, UR3, except U3. That U3 is the Z translational motion. So the impactor is allowed to move in Z direction, up and down. The remaining motion of the impactor is fully constrained in this case. Okay, so that is done. Yeah, we can see the constraint or the boundary of the impactor. Then finally, we have to give the velocity or uh, velocity to impactor. How we can give? We have no experimental data at this time. If there is some experimental data, we will introduce the amplitude data for the displacement pattern of the motion of the impactor. But now we don't have. So that what we can do here is if we can use a predefined field. So Abacus allows us to use a predefined field. So here, create predefined field, initial step, mechanical velocity. So now continue. So I'm going to also give velocity through the reference point only also. This is the reference point. Done. So I want to give the velocity of 2.5 meter per second. So our system is by default metric, so there is no need of conversion. So 2.5, okay. That 2.5 is only given in the V3 value. That V1 and the V2 remain blank. Okay, V1 and V2 remain blank, but V3 is given with, um, you see here, that is, this is the velocity of Z direction. Okay, so the motion is prescribed only in the Z direction that is given here. Okay, so this is the model. This is the boundary condition. So all the boundary conditions, all the constraints required are already defined. Okay, uh, these are the steps. Okay, okay, these are what we have discussed. Okay, okay, yeah, velocity is also given. What's left? Everything done. That V1 and V2 remain blank. Okay, so let's go to generate the finite element mesh. So this is the part which is helpful to um, identify our mesh types, uh, identify to give the element size. Okay, in this we can we can define the element type, the element size, and different conditions. So to specify mesh generation algorithm, that will be be used, select mesh control, then click on plate. So let me do it practically rather than, and I'm going to use the hexa type of mesh. Okay, so this type of mesh I'm going to create with the global seeds of this is coarse mesh, 0. That means 2.5 millimeter is coarse mesh. Anyway, for our simple analysis, let me use us. But if our analysis require too much precision, the mesh size should be very less. And the problem of increasing mesh size is increasing the computational time and the computational cost. So, so let me go to the mesh. Okay, switch to mesh model. Here, uh, uh, I'll mesh each part separately. So for that, seed part, click on seed part. By default, it's 7.5 millimeters. So I will give 2.5. Apply. So then give the assign mesh control. So I'm using hexa structured mesh. Okay, hexagonal structured mesh type, and some other use different mesh based on the algorithms of each of them. And each of the algorithms are already written in the Abacus user manual in internet. You can check for what is sweep, what's the bottom up, what is hexa-dominated, theta, tate, wedge, so on. So I refer you to there, okay? And then mesh, okay, yes. Immediately the part is measured. Now I have to assign the material, the element type. What element type we are going to use? Because we selected there the continuum shell, so we have to select that. And the analysis type. So analysis should be explicit analysis because this is dynamic analysis. Okay, and it is not 3D, but it is continuum shell, linear, and hex. Okay, so now I allow the elements which are damaged during the damage analysis to delete, and then enhanced hourglass control. So these things also are one very big issues to be discussed, but need a separate time. Anyway, I selected enhanced hourglass control, element deletion allowed. So now the created element is SC8R, which is called an 8-node quadrilateral in-plane general purpose continuum shell, reduced integration with hourglass control, with finite membrane strain is selected now. Okay, that is similarly for zero ply. Okay, this 2.5. Okay, then mesh, and then element type should be selected explicit analysis, continuum shell, enhanced element deletion, yes. Okay, then the next is the impactor. So impactor is a rigid impactor, so that selecting the element type for this has no such very big issue. Anyways, let me give the impactor size 0.05. Okay, yeah, this is global seed. Yeah, mesh. This is the impactor after mesh. So the total assembly of the mesh is seems like this. It is coarse mesh. We can redefine the mesh whenever we need, or when it need accuracy of the analysis. Okay. Okay. Now the mesh is done. The next step is the job step. So we have to run this file. Mesh is already done. Yeah, exactly done as expected. And then run the model. That is the eighth step. So select the job model. Now switch to the job model and create the name of the job. I gives impact simulation as a job name, and you can accept the default setting for this. Why? Because uh, in user material subroutine system, we have some options that is not included in this tutorial. In next time, maybe I will add that user material than the already inbuilt system. What I have used here is the inbuilt system. I didn't use some user material system like UMAT, VUMAT, or other thing. So let's go. Okay, so here switch to the job. So now create job. Give the name of the job, that impact simulation. This is the job name. Okay, so here we are accepting all default setting now for this exercise. For another case, we have other options which we can go to user subroutine file, but we are not now using that. So let me go to say okay. Here we can get this dialog box of the job manager. So on the job manager, now we can submit our job. Submit job immediately. Yeah. Now the job is running, not running, but submitted. And as soon as you submit your job, you have an access to monitor or check your whether the analysis is going or not. Yeah, it says analysis is running, means we can monitor the running of the analysis. So here we can see the log, the error, the warning, the output, data file, message file, status file. Different files are here in the monitor box. Okay. So until it finishes running, we can talk on different files which are available in this Abacus system. Okay. So we can monitor. So some briefing in the file types in the Abacus CAE run. What are these? Abacus also create a large number of files during analysis. A large number of files are there in Abacus. These are, you can find them in Abacus work directory. Actually, one thing we made mistake here is we didn't create some folder for this analysis. For that reason, I am going to kill the analysis and assign the analysis to some particular position because I didn't save my work from the very beginning. As I told you, at the beginning of analysis, we must specify some particular folder and that should be in a directory. So I am going to kill the analysis because this is now running. Uh, Running is ongoing. So I will kill it. So here there is an option called kill. Yes, immediately terminated now. Okay, the analysis now terminated. So what can I do? Let me go to file, set directory. So on some particular directory, let me go to D and let me call the directory as Abacus, Abacus training, Abacus training. Okay, where is that Abacus training? Search the Abacus training. Yeah, Abacus training. Okay, okay. Again, file, save as, where? In the Abacus training directory. Impact simulation. Impact simulation. Okay. Now our file is created in the Abacus training impact simulation, that is CAE. So we can now rerun it. We can now rerun the file. So come again and submit again. Yeah, this is the proper way to get all data in one folder. Unless and otherwise, I don't know where it is saved. The previous which I ran might not be easily found because it dispersed in somewhere in computer. So now exactly it is in the Abacus training folder and with the name impact simulation CA. That is what. Okay. So you can find a number of files in the Abacus work directory. Some of these are, for example, impact simulation.imp file. This imp file is an ASCII file that defines the finite element simulation. And this is how Abacus CAE will interact with the graphical user interface system, GUI. That the communication between the Abacus platform with the user is with this system. So we often edit the file and run file with the directly when we use Abacus with some user element or user material subroutine. Okay. Another file is .log file. So impact simulation is the file name of the impact file name or the job name. So .log is one which summarizes the outcome of each phase of the analysis. Another is .start. Actually, this is not the star, but it is the start. Okay, it implies the status of the analysis. So which updates during analysis to show its progress. And another is MSG, that message file, contains error message. The next is .dat file. This dot file contains both error message and the out of analysis. It is sometimes the only way to easily view the results of an analysis that has user element. The next is extracting the output or extracting the result. Okay. Our basic intention is to extract the output or the simulation output, which is located in the visualization module. Okay. After the analysis, at the end of analysis, or once successfully completed the analysis, the next step is extracting data or outputs, different animations. Okay, the counter plots, the von Mises stress, okay, the deflection pattern, and so on. Those things are obtained in the visualization module. Okay, so if you would like to plot contours of variables, you can go to result, field output. The field output menu will always you to select different variables. If you don't see the variables, you will want to plot that. Usually means Abacus didn't save it. That means in the um, step menu, we didn't select proper variables so that Abacus will not generate them. For example, in our analysis, which is running now, I didn't select the damage variables, but I introduced the hashing damage parameters so that my analysis will not give me the hashing damage parameters. That hashing compressive damage, hashing tensile damage for matrix, either matrix or fiber, that will not come in my analysis. So that the current analysis is still running with some error. So what can I do? I did it intentionally to bring back you to the analysis. So to get it, you will need to go back to step menu and use the output menu and add the variables. Then rerun, how we can rerun. So now I'm going to again kill the analysis and go back to, um, uh, yeah. Now this analysis perfectly running. Yeah, it's running, but running with without important output. So I need that output seriously. So I want to kill this and go back to step module. Now terminated again. Okay, let me go back step module. On that, I have to, there is here what you call that field output and continue. So what is there? Um, Failure or fracture. Then I have to initiate the scalar stiffness degradation. Okay, a damage initiation criteria. Okay, and then I may select this fiber tensile damage, fiber compressive damage, matrix tensile damage, matrix compressive damage, shear damage. Okay, so I selected this, and then status must be on here also. Yeah. So this is the method how we can rerun our file, because if we are not getting at the end of running the file, we might not get proper variables of analysis. Then we have to rerun the analysis after selecting those required variables. Now I check the damage parameters and the damage variable. So I will go back to the job and also rerun the job. Okay, again submit. Yeah, okay. So this is the method how we can check uh, our work. So uh, you can change the view to counter plot look by using the options command menu or option counter. Some additional features of the viewport can be controlled using viewport, uh, viewport, viewport annotation option. Actually, this helps you to uh, make a good visualization with some text, um, legends, and other things. Okay, so to modify those things, we use this option. If you want to change the background of the BIF or to view to save loads for report, view graphic option menu that to change the background. Abacus can help also plot graphs showing the spatial or temporal variation of quantities of interest. For example, to plot the contact force acting between the impact and the plate as a function of time, someone go to result, history output, and then select total force due to contact pressure. Again, Abacus CAE also allow you to post-process data. That means once we extract some important data from there, we can use this data in other softwares also. For example, if I want to plot the displacement time curve, force time curve, kinetic energy force time curve in maybe Excel, or it can be in some other software, then I will extract it and uh, uh, save it for the particular file type. So that can be also possible with. And we can make also some XY data operation, and some kind of mathematical operations also can be done on it. Okay, but in practical, the post-process ODB data by we can write it with the Python script. Okay, for further um, uh, parametric steady type. Okay, so you can also plot the velocity or displacement of the center of impactor by using result, history output, and select spatial displacement U3, and then press plot. So this all will be, we can make practice of this thing. So the visualization model has many other features. If you have time, you can check most of them. Anyways, uh, uh, these are actually the outputs of the same analysis I made before. So these are some outputs. This is the U magnitude for composite, and this is the U magnitude for the isotropic material. And just for the same load condition, for the same magnitude of velocity, impactor mass, and the same dimension, but material is one is plate, another one is isotropic plate, and another one is composite. So the first one is the composite plate. Deflection is 8.53. And deflection of this isotropic material is 4.659. So there is large difference in between them. Again, U3, for example, these are the everything the same except material and the stack. One is made from a single plate, another is made from four plate. And material property is given for composite for the first one, and for the second one, aluminum plate material property. So how is the how is U3 deflection? U3 deflection of composite is 8.53, and aluminum is 7.9. Still different. Von Mises stress for composite, it is 1.46446 gigapascal. For aluminum plate, 3.633. It is not giga, even it's very less number. Okay. So such large variation of the contours, even contour variations, the contour plot also different. The pattern, so the two materials are completely different. Okay, so this is the shear stress, 1, 2. And here we can see the Hessian damage because we already assigned the Hessian damage that fracture criteria, strains criteria are fulfilled. So the Hessian fiber compression damage float. Okay, the Hessian fiber tension damage, the Hessian matrix compression damage, the Hessian matrix tension damage are specified. And different floats can be plotted from the analysis. I simply used all floats in one heap. For example, you can see displacement time float. You can see velocity time float. Again here, kinetic energy time float, total energy float. Okay, here the contact force history float with time. The hourglass energy effect, the strain energy, and so on. All are floated here. Okay, so velocity, force, displacement, energy, all floats are here from the particular composite material. So this is all about, and once the analysis is finished, okay, let me see whether what amount is. Actually, it is very late, but I will open the one I have for the same model, for the same parameter, everything the same. So I'm going to open that one, and we can uh, discuss the same the outputs of Abacus. Sorry, this is isotropic one. But, okay, that this is for isotropic plate. Okay. Sorry. I'm very sorry. I forgot where I saved it. Tutorial CA. What is this? Impact CA. Sorry for the delay. Abraham. Yeah, this is the file. Okay, so this is the file completed for the same analysis. So I am going to see the result of this. Okay, this is found in AKE, Abacus tutorial folder, file. Okay, whenever you open, it asks you to go to the directory. Okay, so if it is in another place, you cannot easily open it. Okay, directory is open. Okay, done. Now I can extract result. Result. So this is undeformed shape of visualization. Now we are in visualization module. This is undeformed shape. Okay, this is our model. Okay, you can see it. And we can see the deformed shape that float contours on deformed shape. So we can see immediately the contour shape. So it is continuum shell element and it shows some unusual type. So let me use result, section point, envelope, apply. Okay, now it shows us some proper visualization. On this, uh, we can see different stress. For example, stress is there, deflection, for example, U3. Maybe this is not complete, I think. Yeah, okay, okay. So this is a deflection. You can animate it with this, or there is an animation here. Yeah, this is animation. Okay, we can visualize different U values, deflection values. So these are not visible, so I have to modify it. B4th annotation option, state block, and we have to give at least 12 or some 14 of font size, and give proper font of mm, okay. Let 3 times New Roman font, apply, then you can see it easily. Okay. So we can see hashing damage, okay, from here. Damage, fiber compression. There is no fiber compression damage. It gives us 0, 0 means fiber compression damage is less. Damage, fiber tension, okay, it is 0.8. The damage, that damage parameters from 0 to 1, so it is 0.846. uh, Damage matrix compression. Matrix compression only one means almost matrix compression fully happen. Okay. uh, Damage matrix tension. Look, matrix tension is there at the very um, again. uh, we can see some floats of the go to output database here, job. So on this, you can see, for example, the kinetic energy float. Okay, the time given for this analysis too much, so that it is longer. Okay, the impact displacement, strain energy, force time. This is the force time curve. So this force time curve implies different damage that happened in the structure. So how it shows us the damage pattern? There is some damage initiation point, there is damage propagation point, and different points give different meaning here. Anyways, these are the curves. Okay. Okay. So you can see the velocity curve. Okay. So these all are there, and we can make some uh, operation, that XY operation, XY tools, XY data, create, create. Then we can go to operate on XY. Then we can combine. By default, it gives us the x-axis as time axis. But for example, if I want to see the force displacement curve in the same graph, I have to use this operate XY data option. And then combining them with the combine operation, okay, I will uh, plot it. Okay, for this purpose, let me do that only, and the remaining thing will be, for example, this is force data. So let me add the force to the system and add the displacement. Okay, where is displacement? Add. So I added two things here. Okay. So where I added it, okay. So then I will go to tools, XY data. Okay, create, operate. So the first one is uh, total force due to contact pressure. So I'll select this combine. Combine. The X entry is special displacement, then comma contact force, pressure and friction. Okay, then what can I say? Yeah, these two are there. So plot expression. This is the displacement force curve. This is displacement force curve. So we have unnecessary data that are making this thing, but you can see the displacement time curve properly here. This shows displacement in the x-axis and force in the y-axis. So this is all about the composite modeling, impact modeling. So thank you very much for paying attention. Thank you very much.
Yes, Amit, I'm stopping the recording.
Hello, hello.
Yeah, fine.
Yeah, done now.
Yeah, stop it. I'm stopping the recording. Okay.
Okay. Okay.